Hi everyone, today we will discuss limits for trigonometrical function. So let us start with sine function, cos function, tan function and all that. So here if you see the limiting value of sine theta upon theta when theta tends to 0, that is equal to 1. Sine theta upon theta when theta tends to 0 is 1. Here this theta, it is in radian. You can see theta, here it is C is mentioned, C is for the radian. So sine theta upon theta when theta tends to 0, that is 1. Similarly, limit of cos theta when theta tends to 0, that is 1. Limit again theta upon theta when theta tends to 0, that is also 1. So limiting value of sine theta, tan theta when sine theta upon theta, theta tends to 0, or tan theta upon theta when theta tends to 0 is 1. As far as the cos function is concerned, it is only limiting value of cos theta when theta tends to 0, that is also 1. Now, if we consider this, so all this here theta or here theta, it is in radian. Now, if you consider this limit of sine x upon x when x tends to 0, so it means here it is in degree. So now first we have to change this degree into radian. So if you consider that, so we have 180 degree. If you consider this convergence, 180 degree is equal to pi radian. So x degree, it will be equal to how much? Pi upon 180 into this x. Pi upon 180 into x. So replacing this, you can write this will be equal to your limit when this x tends to 0 sine x degree upon x. So for that we can replace how much? Sine pi upon 180x and divided by this x. Now we will convert this in the standard form, that is sine theta upon theta when theta tends to 0 is 1. But here if you consider this as theta, so sine theta, here we should have theta in the denominator, but just to get that we must have pi upon 180 here. So if you have considered this pi upon 180 in the denominator, this extra term, then we need to multiply this numerator by the same quantity, pi upon 180. Now this entire quantity, this pi upon 180 into x, if it is considered as theta, and then this is now also theta, so sine theta upon theta when theta tends to 0 is 1. Now here pi upon 180 into x, we are assuming theta. So if x tends to 0, as here x tends to 0, this entire quantity will what? Tends to 0. It means in that case also theta tends to 0. So here we are able to justify this relation that sine theta upon this theta when theta tends to 0 is 1. So this part, this entire part, the limiting value of this, it is equal to 1. So 1 into pi upon 180, that becomes pi upon 180. So your answer is pi upon 180. That's what you can see here. So when it is, wherever there is this angle is marked in degree, so first consider or change that degree into radian and then use this standard relation. That is the intention behind this. Otherwise, we always directly use this relation and calculate whatever is needed. Now see the exponential limits, that is limit of a limiting value of 1 plus 1 upon x. These are the standard form. Whenever you observe these standard form, directly you can make use of these relations. So limit of 1 plus 1 upon x to the power x, here it is x in power, when x tends to infinity, you can see 1 upon x tends to 0 when x tends to infinity. So limiting value of 1 plus 1 upon x to the power x when x tends to infinity, this is equal to e. E means the exponential function, that is y is equal to e to the power x. We have that as an exponential function. So limiting value of this, it is equal to e. Similarly, this limit and this limit, they are equivalent to each other. The only thing is, if you consider, suppose 1 upon x is equal to, let us say, alpha. Suppose 1 upon x is equal to, suppose, alpha. So when x tends to infinity, this implies alpha will tends to what? 0. So in that case, alpha tends to 0. So here 1 upon x is equal to alpha. So 1 plus alpha, this x will become what? 1 upon alpha. So you have 1 upon alpha. When x tends to infinity, alpha tends to 0. So we have alpha tends to 0. So this and this That is same. The only thing is we have changed the form. Here it is x tends to infinity, here it is alpha tends to 0. That's why the value of this, or the limiting value of this, it will also be equal to e. So this is e as well as this is a. Now again, a to the power x. E to the power x is an exponential function. In particular, a to the power x, b to the power x, c to the power x, that is also an exponential function. So here you have limit x tends to 0, e to the power x minus 1 upon x, that is equal to ln a. When we write ln a, that is log of base ea. Log of base ea, that is the natural logarithm. Obviously, when it is ln a, so log of only positive quantities are defined, and that's why we must have a greater than 0. So these are the conditions for the logarithmic function. So a should be greater than 0, because finally we are getting this ln a. This ln a means that is log of base ea. So these are some of the standard relation as far as the exponential or trigonometrical functions are concerned. Wherever necessary, we will make use of these relation and we will proceed to calculate our answer. Now there are certain properties or operations on limits, or you can say theorems on limits. So if you have a limit, suppose limit x tends to a f of x, limit of f of x when x tends to a, let us say it is equal to L, and similarly limit of gx, there is another function, suppose gx, so limit of this gx when x tends to a, let us say it is equal to m. Then if you have addition of these two functions, f of x plus gx, what will be the limiting value of that when x tends to a? So this will be nothing but L plus m. That means if you have different functions and we know the limiting value of those functions when x tends to some particular value, suppose a, then in that case, if you have to calculate the limiting value of addition of those two functions, then the limiting value of that, it will be equal to limiting value of the first function plus limiting value of the second function. So that gives you L plus n, means limiting value of f of x plus gx when x tends to a, it is equal to the limiting value of f of x plus limiting value of gx when x tends to a, and that is coming as L and m, because we have assumed limiting value of this is L and limiting value of this is m. Similarly, if you have subtraction f of limiting value of f of x minus gx when x tends to a, that will be same as L minus m. Product of this, so here also it is L into m. Division of this f of x upon gx, so that will be again L upon m. So from this you can conclude limiting value of, suppose two functions are known, let us say f of x as well as gx when x tends to a, then the limiting value of addition of those two functions, it will be equal to the sum of the limiting value of those individual function L plus m. Subtraction, it is just L minus m. Product, it will be L into m, and division L upon m. M is in the denominator, so obviously m should not be 0. So m should not be equal to 0. Now if function is multiplied by some constant k, then the limiting value of that gets multiplied by k. So limit f of x when x tends to a, it will be equal to k times the limiting value of this, k times the limiting value of this, and that is equal to k into this L. If I elaborate it here, suppose you have to calculate limiting value of k into f of x when x tends to a. So this will be equal to your k times this limiting value of f of x when this x tends to a. And we have assumed the limiting value of this as L, so this will be equal to k into this L. So that way we can calculate it. Now see some of the more properties you can say, or some operational method. If you have two functions f of x and gx, and let us say f of x is less than or equal to this g of x, limiting value of f of x is L and limiting value of gx when x tends to a, in both the cases it is m. Then if f of x is less than or equal to gx, then the limiting value of f of x will also be less than equal to the limiting value of gx. So we get L less than equal to m. Similarly, if it is suppose raised to power gx, f of x is raised to power gx, then the limiting value of that new function, the new function that we get is what? f of x to the power gx. In that case, the limiting value of f of x to the power gx when x tends to a, it will be equal to L to the power m. Similarly, if you have composite function, let us say f of gx. So f of gx, this becomes a composite function. So it means the limiting value of f of gx when x tends to a, that will be equal to f of limiting value of gx when x tends to a. Means first calculate the limiting value of this gx when x tends to a, and the net value of this, the final value of this will be f of that function. So f of this function. So limiting value of this is what? M. So value of that, it will become f of m. This m we had assumed, we are discussing under that assumption. So this is equal to f of m. Similarly, if you have log of f of x, limiting value of log of f of x when x tends to a. So log we will take out of this limit. So log of limiting value of f of x when x tends to a. So if it is equal to suppose n, then log of n. As soon as log appears, obviously the condition has to be fulfilled, so that this n should be greater than 0. Again, if you have suppose this inequality, these are some of the special features you can say. If f of x is less than equal to gx, gx less than equal to hx for all values of x, means in the domain, complete domain of the function for all value of x, and limit of f of x is equal to limit of hx, and both are same, and that is equal to L. In that case, the limiting value of this function gx, that is also equal to L. See this inequality, f of x is less than equal to gx, gx is less than equal to hx, and the limiting value of this function f of x and hx, it is same. Limiting value of f of x is L, limiting value of hx is also L when x tends to a. If both are same, in that case, even though there is the inequality here, this function less than this function less than this, in that case the limiting value of the function gx, that will be same as the limiting value of f of x or limiting value of hx, and that will be equal to this L. This is termed as squeeze-play theorem. So these are some of the properties or operations or theorems of as far as the working on limits is concerned, and if possible keep these relations in your mind so that it becomes easy when we start solving problems. Thank you.